So let's talk about the interaction of sunlight with the plants as the sun is coming in to the surface. There are a number of things that happen when the sunlight interacts with plants. We have some of the radiation is reflected. We talk about albedo of anything, the albedo of the snow, but plants also have an albedo. But as you know, if you look at plants outside, they're fairly dark in color. So only about 15% of the sunlight coming in gets actually reflected back to space. Most of the energy actually goes to evaporate water from the plant. 75% of the energy arriving at the plant, the energy from the sun, will eventually result in evaporation of water from the plants. A small amount, 5%, will actually go through the leaves, through the plants, and get transmitted. And also a very small amount actually is used for photosynthesis. Only 5% for photosynthesis, and the actual heating, because this is energy coming in, will actually heat up the leaf. So a small fraction is actually used, not very efficient, the process of photosynthesis, and majority of that energy goes actually to what we call evapotranspiration, the respiration and the evaporation of water from the plants. This also depends on the geometry of the leaves, the shape of the leaves, how many leaves, the density of the leaves. Now, albedo is normally something we talk about the total reflectivity of sunlight, but if we want to see how this varies, the reflectivity as a function of wavelength, then we can look at this plot here, which is going from about 300 nanometers up to about 1,000, or 0.3 to 1 micron. And on the top, you can see that we have half of this plot up to about 700 nanometers is the visible part of the spectrum. And then we enter the infrared part, which we can't see with our eyes, but is the heat also that we feel from the sun. And when we look at green vegetation, there's actually a dramatic difference in the reflectivity between the visible part of the spectrum and the infrared part of the spectrum. We see that when we're talking about the visible part of the spectrum, and that's one of the reasons the plants are so dark in color, normally less than 10%, maybe even 5% of the shortwave, the visible radiation is reflected from the plants. But when we get into the infrared, we see a huge jump, and it goes up to about 30%, the reflection from the longer wavelengths in the infrared. Actually, you also notice there's a little bump here in the visible part of the spectrum, and this is in the green light, the green part of the spectrum. There's more reflection of green light than the other colors, and that's why the plants look green to us. We have more green light coming to our eyes than the other colors in the spectrum. If we just look at soils, dry soils and wet soils, there's a more linear change as a function of wavelength. We see more reflection as we're going to longer wavelengths, but we don't have this very clear jump that we see from green vegetation between the visible and the infrared. If we now expand even further the spectrum, so here we've got the reflection of both on the top soil and vegetation from around about 0.4 microns all the way out to 2.4 microns, and we can see that at the beginning from about 0.4 to 0.7, this is the visible part of the spectrum. Then we get to the near infrared, and then a longer wavelengths or the short wave infrared. And again, this is the reflectivity of green vegetation. Again, in the visible part of the spectrum, not much reflectivity, and then it jumps up in the infrared. But we also have these two minimum here in the vegetation, and this is because we have absorption of water vapor. Water in the plants also absorb certain wavelengths, and so these two dips are actually about the water we have in the leaves of the plant, and so it's not continuously or slowly decreasing as a function of wavelength. We get some ups and downs in the spectrum, and in the bottom we can see the same spectrum but for different types of vegetation which are under different type of stresses. So if we look at healthy vegetation in the green curve compared with the stressed vegetation in red and severely stressed vegetation, implying maybe lack of water or lack of nutrients in the ground or very high temperatures, we see that the height of each of these curves at different wavelengths is slightly different. So for example, the healthy vegetation has higher values in the near infrared than we have, say, in the shortwave infrared. But when the plants are very stressed with no water in drought conditions, then we see the opposite. If we look at the orange curve, we have less visible reflection than we have from the shortwave infrared. And looking at the ratio of these different wavelengths from, say, satellites, we can actually map out whether plants are healthy or are stressed or unhealthy. And one of these indices that we use, and we showed it also earlier on, is what we call the NDVI, which actually looks at the difference between the near-infrared wavelength in the near-infrared and the red in the visible, the red light. So this index is basically a difference divided by the summation of these two wavelengths. And if we see a healthy plant, with the reflection, we have about 50% of the reflection in the near-infrared on the green leaf on the left, and only about 8% from the red light. This will give us an NDVI of about 0.72. And if we look at a stressed leaf or vegetation, then we have less reflection in the near-infrared, a lot more in the red part of the spectrum, and we'll have a much smaller index, 0.14. And in fact, in the laboratories, if we look at different types of vegetation which is also dead, for example, will generally have a negative index. And we can go up with unhealthy plants, moderately healthy. The value of the NDVI goes up and increases as the plants become healthier. And this map we can see here is a satellite image using this technique to try to map out healthy and stressed or dead vegetation. And this is taken from August 1993. In the summer of 1993, there was a huge amount of rainfall in the Midwest and the northern part of the United States. The northern Great Plains caused huge flooding in the Mississippi River. And as a result, we can see that the green areas on the map are where we had very healthy, lush vegetation growing. This appears as the positive numbers in the NDVI anomaly. At the same time, in the eastern part of the US, the brown colors are where we had much below normal rainfall, and we can see the dark brown colors showing heavily stressed vegetation there.